Welcome back to Physics 141 online. I now like to calculate the total rotational kinetic energy of an arbitrarily shaped object that is rotating around an axis that's fixed. So here I have my general shaped object, and the x and y axes indicate that there is a rotation axis perpendicular to the page and passing through the origin. So what we're going to do in order to calculate the entire kinetic energy of the entire object is break it down in little pieces. Each piece we will refer to by a mass delta m sub I sitting at a distance r sub I away from the rotation axis. And so the position of that object at a certain point in time is given by this arc length s at an angle theta from the positive x-axis. And we're going to assume that this object is rotating at a constant angular velocity omega, so that the relationship between v and omega tells us that the velocity of that piece in the tangential direction, of course, as the object rotates around that axis, that speed v is equal to the radial distance r times omega. So we'll use that in just a minute. How do we write down the kinetic energy? It's 1/2 mv squared, right? So this piece of the overall object is moving at a speed vi, and it's got a mass delta m sub I. So the amount of kinetic energy associated with that piece is just delta k sub I, and it's given by this simple equation. As I said a minute ago, that little piece is moving with a tangential velocity v sub I, which is r sub I times omega. And the great usefulness of this relationship comes in when we make our substitution. So we now just substitute v sub I into this equation for kinetic energy, and you see what happens is this term omega is now present, and omega is the same for every piece on the object. V changes because the further a piece of mass is away from the rotation axis, the faster it's moving. But omega is the same for all the pieces. And this allows us, for the entire object, to write the sum of all of the kinetic energies of the pieces, these delta k sub i's, and add them all up to get the total kinetic energy of the object. Now the reason I write down here an approximation for this is that each of these pieces has some finite size to them, right? And so to assume that all of that mass is sitting at a constant distance away from the rotation axis is not quite right, because this piece has some size to it. So it's only approximately correct. And so what we can do with this delta k sub I, put that into the summation, and what can come out of the summation is any term in that expression that's the same for all the pieces. 1/2 is just a constant, right? Omega, now, the argument that I made was that the omega is the same for any point on that object, because if it rotates through one revolution, all the pieces of the object do that in the same amount of time. So omega comes outside the summation, and what's left is the summation of all of these mass elements times the radial distance that those mass elements are from the rotation axis. And what we can do in order to make this expression exact is apply calculus. So in the limiting case where these mass elements become very, very small, then delta m becomes the differential mass dm, and the approximate sum becomes an exact result that's written down using the integral. So the exact result is going to be given by 1/2 times omega squared times, instead of a summation, it's going to be an integral, and instead of delta m, we're going to have dm. So here's what it looks like. 1/2 omega squared, and what I've done is put the dm on the outside, because now we have an integral r squared dm. What that represents is dm is a tiny little mass element, and r is the distance that that element is away from the rotation axis. And what we're now going to do is notice that this summation, this integral, is something that characterizes the object as a whole. No matter what kind of shape it has, this calculation can be done, and it simply represents how the mass is distributed around the rotation axis for that object. Because of that, It's something that's unique to the shape of that particular object, and so we give it a special name. We call that integral the moment of inertia. Some books will call it the rotational inertia, but for historical reasons it's referred to as a moment of inertia. I is the symbol that it's given, and so it's this integral r squared dm. If we use that I with this definition, we can write the rotational kinetic energy as 1/2 this moment of inertia times omega squared. And you'll notice by comparison to the kinetic energy expression for translational motion of a single mass that this looks quite similar. So translational kinetic energy of a mass m is 1/2 mv squared. Rotational kinetic energy for an object that has a distribution of mass around a rotation axis is 1/2 I times omega squared. And it's easy to see how this relationship carries over if we take the translational kinetic energy expression and replace m with the moment of inertia I, and then in turn replace the translational velocity v with the rotational velocity omega, we get the same expression. So I hope you'll see that really what we've developed here, although it's a new equation, it is very, very analogous to the same expression that we had for translational motion. And as we go through this course, this part of the course, we are going to continue to see these analogous quantities. We've already seen how position can be represented in rotational kinematics by the angle theta. Linear velocity can be replaced by angular velocity. Linear acceleration can be replaced by angular acceleration. And now we see that the quantity that plays the role of the mass when we go over into rotational motion is this moment of inertia. Very shortly, we'll see that there is a rotational version of force as well as a rotational version of momentum, and we'll get there in a few days. So the reason I point this out with the table is it helps me to remember the equations. If I remember, for example, that F is equal to mass times acceleration, then if I know what the rotational analogs are for force and mass and acceleration, I can write down a rotational version for Newton's second law by just making simple substitutions. All right, let's look at how we calculate this moment of inertia for a solid object. And we're not actually going to work out the calculations, but just quote some of the important results that come from using calculus to evaluate that integral. For simple shapes, the necessary integrals can actually be done analytically so that the results that we get are exact results. If you have really complicated shapes or irregular shapes, you might have to do a numerical calculation where you can't actually do an integral with paper and pencil. So some of the important results, some of the important shapes listed in our textbook, and there are more as well, but these are the important ones, are for a thin cylindrical hoop of mass m and radius r for an axis that goes through its center of mass. And so if that object, this hoop or ring, has a mass m and a radius r, the moment of inertia through the center of mass is given by mr squared. And that actually makes sense because all of the mass, if this is a ring, a very, very thin ring, all of the mass is at the same distance r away from the rotation axis. Now for a solid cylindrical disk with the same mass and radius, we should expect the moment of inertia through the center of mass to be a little bit smaller because only the very edge of the object has mass at that distance r. The rest of the mass is distributed at smaller distances away from the rotation axis. And when you do the actual integral, you find out that the result becomes 1/2 mr squared. Finally, for a thin rod of mass m and length l, very, very thin like a pencil, when we have an axis through the center, the result that we get when we do the necessary integral is that the moment of inertia around through the center of mass for an axis through the center of mass is 1/12 the mass times the length squared. So those are important results, and there are some others that are tabulated in the book, and you can just use these. We're not going to ask you to calculate these from scratch. But here's the kind of calculation that you might do. What if you have a compound object where perhaps you've got two or more solid masses that are connected together, and then the entire object rotates around some axis. So there's a very, very simple way to combine their moments of inertia when there's a fixed axis, and that is simply to add them up. So the total moment of inertia, if you've got individual solid objects that have moment of inertias I1, I2, and I3 about the same axis, then just adding them up gives the total moment of inertia about that axis. So here's a simple example. Find the moment of inertia of a thin solid rod of mass m and length L with, now here's the additional part, with a small mass m/2 attached to each end. And we want to do this for an axis passing through the center of the rod. So here's the picture. We've got this rod of length L and mass m, and then attached to each end of the rod is a smaller mass m/2. And we're going to assume that it's very, very small, so that we can regard all of its mass at a distance, the same distance away from the rotation axis, which passes through the center. How does this work? Well, the total moment of inertia for this entire object is going to be the moment of inertia of just the rod through the center of mass, plus I1, the moment of inertia of the mass on the left-hand side, plus I2, the moment of inertia of the mass on the right-hand side. So this is pretty easy to do. We remember from the previous slide that for a thin solid rod, the moment of inertia is 1/12 ml squared for an axis through its center. So that's the first term here. I1, if we look at the mass on the left-hand side, it's mass m/2. And what's the distance that it is away from the rotation axis? That's the distance L/2. So m/2 L/2 squared is its contribution, and I2 is the same, right? Because the mass on the right-hand side has the same mass and is the same distance away from the rotation axis as the mass on the left-hand side. So those two terms are the same. You can easily see that this gives us 1/12 ml squared plus 1/8 ml squared plus 1/8 ml squared, and when you do the necessary arithmetic, you get that the total moment of inertia of this entire object rotating about an axis through the center is 1/3 ml squared. You will often have problems where you might have a compound object, and so this simple approach gives us the total moment of inertia. And there's one more example where you might have to calculate the moment of inertia, and that is about a different axis compared to the axis that goes through the center of mass of an object. So here's the situation. If we know the moment of inertia of an object with mass m about an axis that goes through its center, and that's what we've been using in the past couple of slides, we can easily calculate the moment of inertia about any axis parallel to that center of mass axis. All we have to know is how far the parallel axis is away from the center of mass axis. That's why this result is called the parallel axis theorem. And I won't prove it, but just quote what the result is and give a simple example. So if this object has a mass m, and we know the moment of inertia about the axis passing through its center, we can find the moment of inertia about a parallel axis by just adding the quantity m times d squared. This only works when the two axes are parallel to each other. So here's a simple example. If we've got our thin solid rod of mass m and length L, let's find the moment of inertia about an axis that passes through its end, where the x is in the sketch, compared to the center. Okay, we know already what the moment of inertia is about an axis through the center. That's the 1/12 ml squared that we used on the previous example. So now let's use the parallel axis theorem to find the moment of inertia about the axis parallel to the one through the center of mass, but passing through the end. So I at the end, which is what we're trying to find, right? That's the parallel axis. It's equal to the I center of mass, plus in this case, the mass of the rod times this distance d between the two axes. And in this case, d is simply 1/2 the length of the rod, L/2. So moment of inertia about the end, about an axis through the end, is equal to 1/12 ml squared. That's the moment of inertia for the axis through the center of mass. And now this last term, you can see it reduces to 1/4 ml squared. And when you do the necessary arithmetic, you find that the moment of inertia for the axis passing through the end is 1/3 ml squared. It's larger than the moment of inertia passing through the center, and you should think about that. Why is it larger? It's larger because if you have the axis passing through the center, then all of the pieces of the rod on the left and on the right are closer to the axis than they would be if the axis were at the end. If the axis is at the end, then of course you have half of the rod that is within a distance L over 2, but the other half of the rod is at a distance between L over 2 and L away from the axis. And in the moment of inertia expression, remember that mass pieces are weighted by the square of the distance that they are away from the axis of rotation. And so that's the qualitative explanation for why the moment of inertia for an axis about the end is larger, in this case by a factor of 4, larger than what it would be for a moment of inertia about the axis through the center of mass. So think about this concept of moment of inertia, try to get some qualitative understanding of it in addition to these quantitative cases. Now, why do we bother with all this? We might like to do problems like this. Here is a simple example, again using this idea of a thin rod of mass m and length L. Imagine that it's pivoted about an axis perpendicular to the rod running through the end. That's what we just did the calculation for. So if this rod is positioned vertically and then just given a tiny nudge, it can swing around so that the rod that started out vertically will swing down, and let's imagine we give it a nudge to the right. It'll swing down in the clockwise sense and eventually reach the orientation where it's vertical again, but where the rod is now below the rotation axis, and it'll look like this at that point. And we might like to figure out, if we give it that initial nudge so that it essentially starts from rest, it starts from a very low speed, what would be the maximum rotational speed that it would have? Of course, we can see that it makes sense. The maximum speed would be when it's in this vertical position shown right here. So how would we do that? Well, we can do that as an energy conservation problem, except you'll notice that the rotational kinetic energy is the quantity that we need to use here, because every piece of the rod is moving not in a translational sense to the right or to the left, but it's moving in a rotational sense around the fixed axis. And so instead of 1/2 mv squared, we would want to use 1/2 I times omega squared in order to calculate the kinetic energy of this rod. We'll finish this example off in class, but it's a great example of a simple problem where we need to know moment of inertia in order to do the analysis. Hope this is helpful, and I will see you in class.